Okay, so we're going to take it a step up a notch and go back to everyone's favorite kind of questions where we look at blocks attached to strings. Okay, so example 2.3.2 says the static friction on one block is holding another block up as shown in figure 4. Okay, so both of these blocks are stationary. Okay, block A has a weight of 6.5 newtons and sits on a table and is connected to a wall by a string. Block B has a weight of 2.8 newtons and is attached to the string that is connected to block A's string at point P. The string from block A to point P is horizontal. The magnitude of force of friction on block A is 1.4 newtons. So, A asks us to draw a free body diagram, of block B and determine the magnitude of tension in the vertical rope. B says draw a free body diagram of block A and determine the magnitude of tension in the horizontal rope and the magnitude of the normal force acting on block A. And then C says draw a free body diagram of point P and calculate the tension in the rope that is now at the angle. Okay, so for A, I know it's weird, but A, we're actually looking at block B. Okay, so if we think about block B, the two forces that we have is we know force of gravity is going to act down. Okay, and we're ignoring everything else in this diagram other than that string here, because this is the agent that is actually pulling on B in this case. Okay, and that's the big part that we have to remember, is that this is the only agent that's actually acting on B. So we only have one force that is acting up, and that is the force of tension from that vertical rope. Okay, now if block B is not moving or stationary, we know that these two forces have to be equal to one another. So for part A, if we are not moving, we know F net is equal to 0. We also know that in this case, our F net is going to equal the force of tension minus the force of gravity. So the force of tension in the vertical rope is simply going to equal the force of gravity that's acting on block B. Okay? And they've given us in the problem. So remember, the weight, so block B has a weight. Remember what weight means. Weight is your calculation of Fg. Okay, your weight is how much that gravity affects you. Okay, so for the force of tension in the rope is going to be 2.8 newtons acting up on the block in that case. Okay, and that's it for part A. You can see just by drawing the free body diagram that once we have the weight of block B, the force of tension at that point, or acting on B, is going to be equal to that force of gravity. Okay. For part B, now we're looking at block A that's resting on the table. So we have some table, and block A is resting on it. Okay. So because we're sitting on a table, remember what we're going to know is that force of normal in this case is going to have to equal that force of gravity that acts down on it. Okay. So we've already kind of been able to solve for that first part of that question. Well, if we look at the vertical direction, we want F net to equal 0. And in this case, Fn minus Fg equals F net. So our normal force is just going to equal what the force of gravity acting on block A is. Okay, and they told us that right up here, that block A has a weight of 6.5 newtons. So the force of normal that is acting on block A is 6.5 newtons up. And now we want to determine what that force of tension is. So now we need to look at the F nets in the x direction in this case. Right? So if we look at the two forces that are acting on A, we know we're going to have some force of tension that wants to pull it in this direction. Okay, and then we're going to have some force of static friction that's acting in the opposite direction to keep it on the table. Now, again, if the F net in that direction is 0 because our block is stationary, these two forces are going to have to be equal to opposite to one another. So, if F net in the x direction, I'm going to say anything to the right in this case, is positive, then we're getting the force of tension minus the force of static friction because it's acting in the opposite direction. So, the force of tension in the horizontal rope is simply just going to equal what the force of static friction is. And again, they told us that in the problem here, that the magnitude of the force of friction on block A is 1.4 newtons. So our force of tension in the rope is 1.4 newtons to the right. Okay, and that's it for part B. Now for part C, what we want to do is we're looking at the point P. Okay, so what we need to do is we need to look at this point here and look at all the forces that are influencing it. Okay, well, pulling it down, we know we're going to have the force of tension in that rope that acts on B. Okay, and that's what we just solved for. Pulling it to the left, you know you're going to have that force of tension that acts on A. Okay, these are just Newton's third law pairs here. Yes, we solve for the force of tension in the rope in the opposite direction, but now if we're looking at point P, block A is going to pull on point P as point P pulls on block A. Okay, and then the last piece of, or last tension that we have is this rope right here, this rope at an angle. So I'm going to call it C. Okay. Now you'll notice that that acts at an angle. So what we're going to have to do here is we're going to have to break up our into those vector components. Now, you know you're going to have some FTC in the y direction and some FTC in the x direction. Okay. Now what you need to think about is notice the direction that these two vectors are going. This one's going to the right and this one's going up, where the force of tensions that we had here were going to the left and down. So if everything here is to remain stationary, then all these forces have to cancel out. So what it means is the force of tension in that third rope in the y direction is going to have to equal what the force of tension in the rope acting on B is. So the third rope in the y direction is simply going to equal 2.8 newtons in that up direction. Okay, now look at the x direction. Notice if it's not moving, we still want F net to be 0. So this force of tension in the x direction has to cancel out with the force of tension that acts on block A. Okay, and that horizontal force of tension is 1.4 newtons to the right. Okay, now that you have your x and your y, it's putting it back together the same way we always have. Okay, so to find that total force, the magnitude of that force is going to be the x component squared plus that y component squared. Okay. Again, we've done this enough that I think I'm just going to go through and simplify. Okay, so I get the root of 9.8 newtons squared, which comes out to 3.1305 newtons. And then we want to find that theta. Remember to compare it to the horizontal. You're always doing y value over the x. Okay. This gives me an angle of 63.43 degrees. Okay. Notice here in this situation, they haven't really given us much in terms of direction, so we're just going to say, yes, I know normally we would switch it, but this is going to be called the horizontal, so I'm just going to put the direction of the force in terms of the horizontal. Okay, so the force of tension that we see in that third rope is going to equal 3.1 newtons at an angle of 63 degrees above the horizontal. Okay, this is Wanny signing off, and may the force be with you.